This is John Black, super chemist, to guess on the mechanism to change a nitro group into an amine group through metal acid reduction. Here's a generic equation for it. You start out with your nitro group. You add 2 electrons, 2 protons, minus water. You get your nitro so. You take that, and again, add 2 electrons and 2 protons, this time no loss of water, and you get your N-substituted hydroxylamine. Then you take your hydroxylamine, and again, you add 2 electrons, 2 protons, and this time you're going to lose water again, right? Proton goes to the water, it comes off, and another proton comes on here after you get your electrons on, right? So you can have your NH2. So that's the generic equation. Let's try to go over the mechanism, though. Remember, we want to protonate first 2 times in 2 electrons, right? Protonation is the quickest thing, so we're going to do that first. You can see that the nitro group becomes a Zwitter ion, and you have a positive nitrogen and a negative oxygen. So obviously, the proton's going to go onto the negative oxygen with all those lone pairs. When that happens, you end up with this, right? You got your hydrogen onto the whatever. Now your nitrogen is still positive, right? You took your negativity away by adding a proton, but you still have this positive part here on the nitrogen, right? Because it should have 5 electrons. It has 1, 2, 3, 4. So it's positive. So we're going to add 2 electrons. 1 electron to make it into a free radical, and another electron to make it negative, right? Now the oxygen is right next to this, right? So the negativity is going to want to, it's more electronegative. So the negativity is going to want to jump up there. That double bond is going to jump up, right? You end up with this. The double bond jumped up. Now you have negativity up onto the oxygens. And you replaced your lone pair on the nitrogen is now back. See how it's back? And you have 1, 2, 3, 4, 5 electrons. So that makes that neutral. Formal charge is 0. Of course, you have a negativity here. We already added our proton and our 2 electrons, so all we have left is to add a proton, right? We added on to the negativity of the oxygen, just like we did on the first step, right? And we end up with this. We end up with the geminal diol on a nitrogen group, on a nitrogen atom. Now I want you to think about this. When you have, let's say, formaldehyde, right? And this would be a carbon instead of a nitrogen, right? When you have formaldehyde and you put it in water, it becomes methane diol, right? The carbonyl group splits off into 2 diols, a geminal diol, right? And a geminal diol on a carbon atom is the same exact thing as a carbonyl group, right? Because what will happen is one of these hydrogens will come over here, right? The water will come off, and the electrons from that proton that came off will come down to form this double bond, just like when you do it with a carbonyl. If this was a carbonyl, think about it. Let's say this was methane diol, right? And this was a carbon. Same thing happens. Hydrogen comes over here, this comes off, and this comes down to form the double bond. You'd have your carbonyl back. But since it's a nitrogen, same thing happens, but when you get done, you have a nitro so. Instead of a carbon with a double bond to an O, you have a nitrogen double bond to an O, right? This is called a nitro so compound, all right? You can see the water is here. It's positive. It came off, leaving your nitro so group. Now this is neutral, right? So we did our protonation, 2 electrons, protonation. We lost our water right here. And this right here is internal. You know what I mean? This to go from the geminal diol to the nitro so is internal. So we did our first thingy. 2 protons, 2 electrons, minus water. And we got nitro so. Okay, so now we got our nitro so compound right here. And we're going to 2 protons and 2 electrons again. This time no loss of water, all right? We're going to protonate. There's a lot of lone pairs would probably go into the oxygen since it's more electronegative than the nitrogen, and you end up with this. And you can see you got an oxonium ion here. Oxygen should have 6 electrons. It has 1, 2, 3, 4, 5. So it's positive. So it's going to grab some of this electrons from this double bond probably, and you'll end up with this compound. Now the positivity is on the nitrogen, because nitrogen should have 5 electrons. There's 1, 2, 3, 4. So it's positive. Now, I learned this from the organic chemistry tutor. You can't have the nitrogen be negative. So at this point, you're going to have to add single electrons, right? So you add an electron to your nitrogen, and you end up with this. Your nitrogen is now 1, 2, 3, 4, 5. It is now neutral, okay? But it still has these lone pairs and stuff. So it grabs a proton, and then you end up with this. The lone pair has a proton on it, and you still have this single electron. So you add another single electron onto there, and you end up with your N-substituted hydroxylamine. But you can see we still added 1 proton, then we added 1 electron, 1 proton, 1 electron. So there was 2 protons and 2 electrons total. All right, so now we have our hydroxylamine. And again, we need to add 2 protons and 2 electrons. We're going to add the proton first, obviously, to the hydroxy group to make a water group. And then this electrons will jump onto the water group, and it'll leave as a neutral water group. And you'll be left with this RNH, just like over here, RNH. The only thing that happens is the water left. But you did protonate, and the water left neutral, so that positivity has to go somewhere, and it goes right here because, look, nitrogen should have 5 electrons. It has 1, 2, 3, 4. So it's positive, okay? Now, we can't add 2 electrons because nitrogen doesn't like to be negative. And I learned this from the organic chemistry tutor. Yeah, you can't add two electrons at this point. So I'm going to add 1 electron, okay? And that will make this, neutral overall. You'd have, because nitrogen should have 5, and it has 1, 2, 3, 4, 5 electrons. So it has a formal charge of 0, okay? Now here it is down here, same thing, right? We're going to protonate these lone pair. Even though this is neutral, it has a lone pair sitting there. The proton can jump on that lone pair. What happens is you get this. Now you got your methylamine, right? But your nitrogen, and only because the 2 lone pairs on one of these hydrogens, you're left with a single electron, right? That leaves us 1, 2, 3, 4 electrons around the nitrogen, and it should have 5 electrons, so it's positive. And when it's positive, you can add electrons. So you add 1 electron, and there you go. You got your methylamine. Now, if there's hydrochloric acid in solution, obviously a proton will jump on these lone pair, and you'll get a alkyl ammonium cation, and then the chloride would be the counter, ion, the anion. But my point is, on this last one, we protonated 1 electron, protonated, added another electron. So we still gave 2 protons, 2 electrons, but we split our electrons up this time. And we did lose a water molecule. But anyways, this is my guess. Funzal. Now, my hero, the organic chemistry tutor, he actually does this mechanism, and he does his different, okay? I really have faith. I mean, he knows more than me. The guy, probably forgot more about chemistry than I will ever learn. But I really think that I am right about this, especially this part. This is where, the first part we agree on. But when it gets to this part right here, okay, he uses an outside source to protonate this to get the water molecule to leave. So over here, he ends up with the water molecule leaves, and he ends up with an OH here, an OH. All right, I don't agree with that because of the way a carbonyl compound acts. This is so analogous to that, it's unreal. If this was a carbon instead of a nitrogen, everyone would agree that this would break down into a water group leaving and a double bond between the carbon and the oxygen. This is the same exact thing except it's a nitrogen. And it has to come out to the water leaves and the nitrogen forms a double bond with the O, forming the nitro-SO compound, just like it would form a carbonyl compound if this was a carbon. All right, I have it like this so you can see the whole mechanism at one time, okay? And I'm going to put a link to the organic chemistry tutor's video about his mechanism, and that way you can compare the two mechanisms and see which one you think is right, which one you think is wrong, etc., etc. Keep in mind, I don't I'm not putting this up saying I know more than the organic chemistry tutor, blah blah blah. He obviously knows more than me. He's probably graduated college and etc. And it's just not about that. But in this particular case, I actually think that I am right, especially when it comes to this part right here, making that it's internal. It's so analogous to a carbonyl compound that turns into a geminal diol when it's in water. You know what I mean? It's just so analogous that to me it has to be this way. I think this entire mechanism is correct. But like I said, I'll leave a link to his video, and he's great. He's like the king of mechanisms. So I'm proud of myself that I could, even if I'm wrong, I'm proud that I could at least understand everything he's saying, and not only understand it, but have a logical argument to why he might be wrong. You know what I mean? Because he's like an Einstein type guy in chemistry compared to me. You know what I mean? Keep in mind, I attribute pretty much all my mechanism skills or logic thinking about mechanisms to the organic chemistry tutor. As a matter of fact, pretty much all of this mechanism is, I got from him. You know what I mean? There's only one change that I changed that kind of changed it overall, was that carbonyl analogy to the geminal diol on the nitrogen. So that kind of changed it up a little bit, but the thinking of it, or was all him. You know what I mean? Everything on here was him except for that one thing that I think is wrong. So like I said, he's the king of mechanisms. Like I said, I attribute most of my skills and logic and thinking about mechanisms to this man. So check out his mechanisms and mine, and see what you think is, which one you think is better. Now, on my mechanism, I lost 2 electrons, 2 protons, 2 electrons, 2 protons, 2 electrons, 2 protons. That's 6 electrons and 6 protons total. Now, the organic chemistry tutor, he loses 6 protons just like me in his mechanism, but he adds 8 electrons. He uses 8 electrons, whereas I'm only using 6. So that is different. And also right here about where I was saying this is analogous to a carbonyl in water, where it would be an internal thing where the proton would jump over here, water would leave, and you'd end up with your carbonyl or your double bond. In this case, it would be a nitro-SO double bond. But anyways, let me know what you think. If it's got any thoughts or whatever. Anyways, Enzo, have a great day, and always remember, science is great.